Thank you, Jeliko, for your kind introduction, and thank you for the organizers for inviting me to this conference and giving a plenary talk, and also for the comfort which is associated with such an invitation. And this comfort would have more earned my co-worker here, which I want to mention at first. This is Alexander Bosch. He's now working at MTU Aero Engines in Munich. And what I wanted to present here in this conference is, to a total extent, I should say, his work during his PhD phase on my chair. So I could not resist to go back 35 years or so, where we were confronted with this topic of variable amplitude loading and life prediction under this loading situation. And at that time, in the year 1986, this was actually the first publication where I was mentioned as a co-author. And the problem at that time, and still is, if you have a variable amplitude loading sequence characterized by, for example, with these spectra, cumulative spectra of exceedance of some levels, maybe a parabolic shape, which is common in automotive industry, or with a so-called straight line shape, which is characteristic, for example, for offshore applications, then you may want to perform a prediction of crack initiation life with a local strain approach. And at that time, and still, you see results which are detrimental in terms of the number of predicted cycles to crack initiation to the experimentally determined cycles to crack initiation. And if you could look on these bars, you will find factors in a good case of 2 on the non-conservative side, going up to more than 10, approaching 100. And so the situation is a bit worse for the straight line distribution than it is for the parabolic distribution. And an even as old idea is to ask fracture mechanics whether this technology or this approach is better to arrive at more accurate predictions of lives to crack initiation. And the simple idea is to go to Paris-Erdogan simple law of crack growth and perform crack growth calculations. And if you do so, and start at an initial crack length, you get the well-known crack growth curves. And if you apply a high amplitude to your structure and to your material, you end up with a short life to fracture. And fracture is defined here as a given and constant length of a crack. Here in my application, it's a crack initiation of a millimeter or something like that. And if you apply a low amplitude, here sigma A3, then your life is obviously longer, and you end up with a longer life N3, and you can plot your lives besides the applied amplitudes, and this is the conventional stress life curve, constant amplitude stress life curve. And this is easy to be performed, and now if you are able to do these calculations, then you can have the idea to apply it for variable amplitude loading situation and start, for example, with large amplitudes, and then you calculate the number of cycles you apply and arrive at a crack length, and maybe at that crack length you shift to a low amplitude and apply some cycles, N3. And you may want to go back to immediate value of cycles or amplitudes, and you have another number of cycles until failure is reached. So, however, this is not the real end of the story, because you can replot these graphs here from fracture mechanics in a normalized way, take each of these crack growth lines and divide them in the life axis here by its end value. And if you do so, the fracture mechanics tells us that you end up only with one line. And if you have this situation, we call that affine damage growth curves. And in this situation, we can repeat our experiment. And this experiment now, is application of N1 cycles with a large amplitude. And in this graph, this means that you apply a ratio of lowercase n over uppercase n, and you end up at the very same crack length. Then you continue with cycles of sigma A3 amplitude, and then with the rest of the thing, then you see in this graph that you have only the chance to start at 0 in the normalized life usage ratios, and to end up with 1, and this is simply Palmgren minus damage accumulation rule. So simple application of fracture mechanics will not solve the problem, because the results are totally identical to a minor damage sum calculation. So what else could we do? So sequence effects and all these things must have other physical reasons, and this is what we are trying to cope with in our extensions of these damage accumulation calculations. Why should we be motivated to take this subject again in our considerations? This graph, which you can take easily from this open homepage here, shows us the electricity consumption, which is here, even in midwinter terms or times, it is nearly totally covered sometimes on noon times by intermittent and renewable energies. And those who are sitting here in front may identify this red line here. This is the energy consumption, and the others are what is supplied. And here at that instant, you need only such a small amount of energy from usual power plants. And if you wait an hour or two, you need this detrimental amount of coming from conventional or nuclear or whatsoever power plants. So, and as we feed in renewable energy in our grid systems, this has the consequence that power plants are operated very differently than they have been designed for. There are many, many more cycles coming from many more start-stop cycles and intermediate lowering of energy and increasing of energy. And there is a certain fear of having not designed power plant components in an appropriate way. And some people wanted to know what is now the life of power plant components under these new load sequences. Never thought of that components should suffer under these conditions. And especially here in our project where I'm reporting to, the people were interested in a spectrum, which is shown here as this blue line here. Actually, this is one shutdown cycle of a nuclear power plant in Germany. And this shutdown will never occur anymore, so I'm free to show that because this plant does no longer operate. You know that we in Germany take all of the nuclear power plants off the grid. So, for example, this spectrum here consists of roughly 100 cycles with a large amplitude. So the amplitudes are normalized here. This is the largest one. And there are roughly per large cycles 100 smaller cycles with smaller amplitudes. So that's the spectrum looks like that. And it is something which is more or less in between a straight line distribution and a parabolic distribution, which I have shown in my first figure, and the number of cycles in each step here you can take from this table. So coming back to fracture mechanics and fatigue crack initiation, it is well known and a good idea to study what has happened before this crack has initiated. So other than we just heard in occurrence under brittle fracture, we know that this incident of arriving at a technical crack of a millimeter size or something like that, there has been crack growth in the stage before that. And if you are happy enough to have identified photographs of the site of the crack initiation of a technical size in an earlier stage of the life, you will be able to simply identify this crack has been there for nearly the complete lifespan. Yeah. And well, I'm very much in favor of accepting that there is crack closure and crack opening. And crack closure and crack opening, as we understand it, is one driver of our nonlinearities and for sequence effects, especially in this stage, but also in the long crack stage, which I'm not really talking about today. So in this schematic sketch here, you see an initiated crack of nearly 0.5 millimeter or so. And what we did is we mounted a strain gauge as closely as possible behind this crack here, and monitored what happens if you apply to this material under strain control, and I should say global strain control, some elastic plastic deformation which causes this crack to initiate and to grow. And on the right hand side you see without a crack you would produce a conventional hysteresis loop looking like hysteresis loops are looking like. However, if you have a crack growing here, these hysteresis loops deform, and especially they do that in the tensile half of a cycle. So the strains measured by this tiny gauge are becoming smaller and smaller the larger the crack grows. And here in the compressive half of the cycles, this lower reversal point remains unchanged where it is, as if no crack would be there. And you will able to identify locations where these loops deviate from one another and where they come together to one loop branch here. Well, we are totally sure that at that position the crack flanks lose contact and they gain this contact again at that position. So we draw here a vertical line here, and this line discriminates in these loops those states where the crack flanks are in contact and those states where the crack flanks are no longer in contact. And these are the effective ranges, and we believe that the effective ranges drive the crack further. I have this is a figure for applied strain amplitudes of 0.5%, and this is a figure for a smaller hysteresis loop, and applied strain amplitude is here only 0.2%, but the results are practically identical. The loops are a bit narrower, but you identify here the crack opening stress and the crack closure stress, and you can identify a more or less vertical line in this graph to distinguish between open and closed. And keep this figure a bit in mind, because now I perform a variable amplitude loading, which consists of a large cycle, which we have seen previously, 0.5% amplitude, and interspersed I have applied the small cycles of an amplitude of 0.2%, which we saw just before. And if you see the measuring signal here, then you see that these small cycles during their complete range are totally open, and the total range can apply or can cause fatigue, crack growth, and such it is. And this is a sequence effect occurring in this stage. The crack driving force, we have chosen to apply Dowling's version of the cyclic J integral, and there are nice formulas which are so easy that you can perform calculations also for 1,000,000 cycles. And this formula simply applies for a semicircular crack in an infinite body, and it consists of that part in the brackets here where mechanical quantities as stresses and strains appear, which are the stresses and strains in the situation without crack, and A is simply the radius of this semicircular crack. So there are two factors, a crack length related factor and a factor from mechanics which does not contain any crack dimension, and we call that in brackets a damage parameter, similar as the Smith-Watson-Topper damage parameter or so, and we call that P index J, and it's based on a cyclic version of the J integral. And these two components here can be attributed to strain energy densities in the uncracked situation, as shown here in these colored lines. And I should mention that the crack opening stress here is taken from Newman's approach, from Newman's well-known equation. And just to repeat, we identify opening and closing along a vertical line. So we have only one history variable in our simulation, and this is the current location of the crack opening strain. And the sequence effects come in a way that, for example, here in this animation, there is a large cycle. This large cycle determines where the crack opening strain is positioned. And if you have this large cycle followed by smaller cycles, these hysteresis loops, then these hysteresis loops produce new crack surface, and this new crack surface can move the crack opening strain more or less slowly or quickly, and this has to be determined to a position which is associated with the smaller cycles themselves. So as I said, crack driving force is J-integral, power law similar to the Paris law, now formulated in the delta J. Keep in mind that the damage parameter is simply delta J divided by A, and well, the crack is assumed to start as an initial crack length, and you have to define the final crack length, and then you can integrate that power law here. And if you integrate that power law and normalize the crack growth curves by the end value, then you again end up with an affine crack growth curve or damage growth curve, which means that in this case you can apply linear damage accumulation now expressed in terms of constant amplitude life curves in terms of J, of this PJ parameter. And one extension is related to the threshold behavior. We do introduce the threshold in J, and we can decide, and we do decide whether a cycle appearing provides a delta J which is larger than the threshold, then it contributes to damage and crack growth, and if it's smaller, it does not. This means that with increasing crack length and damage, the endurance limit of the material and the component is continuously decreasing. So now I come back to our investigation of the current project I'm reporting on. These are the specimens which we tested, so unnotched hourglass and smooth specimens, specimens with a notch and even welded joints. And I have to appreciate the work of our co-workers at the Fraunhofer Institute on Material Mechanics in Freiburg, who did a lot of the experimental work and also own modeling, and they will report that at any other occasion. And well, I took also their experimental results and performed calculations. Not I, Alexander Bosch did that. So the load sequence we are interested, I already introduced it. It is shown in this table here, in the middle of the last line here. So this is a pseudo random sequence associated with the spectrum I've shown. And what we did is that the small cycles are not interspersed only in the middle here between the largest and the lowest strain, but although we hang it up on the upper reversal point, or we shifted it to the lower reversal point, we took the spectrum and applied it in an ordered manner, going upwards, downwards, upwards, downwards, again shifting smaller cycles up or low in order to identify what is the effect of mean stresses or so. And finally, we performed a lot of two-step tests consisting only of a large cycle here, large amplitudes, followed by a number of small amplitudes, either at the upper reversal point, the lower, or somewhere in the middle. And we varied the amplitudes of the large and small cycles, especially the small cycles amplitude were chosen to be either just above the endurance limit or just below the endurance limit. And the number of these cycles are also varied between 10 and 10,000. So finally, this campaign had 70 experiments with constant amplitude loading and 124 experiments under variable amplitude loading. So the constant amplitude loading provided us with SN curves and the notch effect and the cyclic stress strain curve and all these nice things, which you must know in order to perform such calculations. Also the cyclic hardening and softening of the materials and so on, and whether there is massing behavior or not. And the variable amplitude loading have been taken to validate various damage models, and some of them I will report in a few minutes. You remember two-step tests, ordered 8-step tests, and random operational loading tests. And again, we measured cyclic hardening, mean stress effects, and minor type damages, which are going down to values of 0.1 only, so meaning a factor of 10 on the unsafe side. So I should mention that not only what I have explained shortly a minute ago, this PJ approach has been performed by others also. I will not have time to go into details here, but I should mention that our research partners in Freiburg very much rely on their damage parameter. And the main difference is that they say the crack driving force is the cyclic version of the crack tip opening displacement, and we say it's a J integral, but there are relations between both, and the differences are not too large. So we developed new models, and new models, oops, this was one too much, were introduced in that way that we now perform real crack growth integrations cycle by cycle and no longer damage accumulation. When doing so, we could modify our crack growth law from the simple power law to a law which includes also the threshold in the crack growth rate calculation. And this has some advantages because we do not have any longer this knee point here in our crack growth rate equation, but we have a smooth transition from the nearly Paris regime into the threshold. And this means that our life curves, constant amplitude damage parameter life curves, do not have a knee point, but a smooth rounding into the endurance limit. And these are the basic data. And here in this graph, I have also included the information on which material we have been working on. This is an austenitic NIOP stabilized steel, the steel which has been used very frequently in German nuclear power plants. And as the power plants go off the grid this year, well, in this application it will no longer be used. Yeah? So this is a well-known, tested and well-tested material, so we know a lot of it. So the main new thing we introduced is the crack growth dependent delay of crack opening strains. I'm going to explain this here. So here in this sketch, we have a large cycle. You see it here at the beginning, followed by small cycle. And as I tried to explain previously, the crack opening strain slowly approaches the value which is associated with a small cycle. And in previous application, we used an exponential law here and used the minor type damage contribution to model this curve here, but this is physically actually not correct, and we shifted that, and we introduced that this curve of changing crack opening strains is associated with a new build crack surface. Yeah? And at the beginning, where the cracks are short, the buildup of new crack surface is very, very slow, and then this curve is flat. And in the later stages of the life, with a longer crack, the new build crack surface will be fast, and with it, the approach to the new stabilized level will also be very, very fast. So this is the change. So transient crack closure means that in the meanwhile, it has become clear that at the very beginning of crack growth, the crack is completely open. There is no crack wake. So this is only constant amplitude considerations. So if we really start our crack growth calculations at the crack length A0, You can distinguish here in these sketches maybe two cases. So if the build-up of the crack surface and with it the crack opening level here is very, very slow, then you can identify in a graph where you plot the associated delta J integral over the crack length that although the effective ranges here become smaller and smaller due to the longer crack, the J integral is continuously and monotonously increasing, and you are faced with this situation as sketched in the upper figure here. However, if this process is taking place very quickly, then the effective ranges are decreasing also very quickly, and you end up with a situation that with the growing crack, the delta J integral is decreasing and it can fall below a threshold value, and then you have crack arrest. So, and this can be done in the modeling by introducing a simple exponential equation here, and you can choose an appropriate reference length which steers how fast this approach is modeled here. So, and this leads us to the possibility that we can reproduce such well-known situations as shown here, that for example for short cracks you can find crack growth even below the long crack threshold, and the cracks come to an arrest, and sometimes if the amplitudes are higher you can pass this barrier. So this is now included in our modeling. You may have seen that we have tested our material under 180 degrees Celsius, which is the mean temperature in the reactors, and the temperatures go up and down between 50 degrees and let us say 350 degrees. So the question was also concerning the temperature dependency on that crack growth. I will not focus on that. This temperature, having different temperatures for different ranges or so, will cause another sequence effect. And taking this into account, we rely very much on the results of our research partners. Their postulate and hypothesis is that if you have a crack tip opening displacement, no matter what temperature is actually present in your material, you will have the same amount of crack advance. So the crack advance expressed in terms of the delta CTOD and the crack growth rate is independent from temperature. And we took that assumption, and this leads us, where we are going to the delta J integral, to the necessity that we have to readjust our crack growth rate equations, because the yield stress or cyclic yield stress relating these both quantities together is of course temperature dependent. So now this is the equational stuff. We performed a lot of calculations. We started with calculated stress-strain amplitudes using massing memory behavior, conventional local strain approach. I will not show these results. They are as bad as they have been 35 years ago. Then we took the real strain amplitudes from our test and assumed massing. Accuracy is a bit better, but not reliable. Real strain amplitudes and corrected mean stresses. You remember that we have put our amplitudes to the upper reversal point and the lower reversal point. We are punished with mean stress relaxation effects. If we take the mean stresses from the experiments, things are becoming better, and the only report here will be on the real strain amplitudes. No machine uncertainties in the control circuits, and other things are then incorporated in our comparisons, and corrected mean stresses are taken into account, and this improved delay behavior of crack opening strains. And this is what I'm going to show now. And I start with the distribution of these ratios of calculated to experimentally determined lives. And again, if the numerically determined lives are larger than the experimental ones, then you are on the non-conservative side. And Langer and Minor means this is the approach which is laid down in German rules on how to calculate variable amplitude live, as far as they told us. And this is, in the average, it's on the unsafe side. So the mean value is 2.7, and this is our German scatter value. It's simply go into this cumulative distribution here at the value of 90% of exceedance, take out the abscissa and go in at 10% and divide these two values. And if this value is high, it's bad, and if it's 1, it's perfect. So PJ original, this is what I explained at the beginning of my talk, which is, by the way, now we have a guideline in Germany for mechanical engineers and performing assessment of strength, FKM guideline. Some of you might have heard about that. And this is now part of this FKM guideline, and these two results have been expected. We know that this PJ modeling is conservative and reduces scatter a bit. Yeah? And our new approach, the results are here in this full black circles here. The mean value, not to be astonished, is now perfect, and the scatter is small. And the message is we will not be able to improve the accuracy here at all. I will replot in the next figure these numbers here. Keep in mind this is 3.5 or something like that here, and this is 0.5. And if I replot all these numbers, not on the abscissa but here on the ordinate here, and I plot these numbers over the number of calculated load cycles to failure, then I get these stars here, so this scatter band. But here in this figure, I have also included constant amplitude testing results with these open squares here, these ones, and there are some dots over there, spread it over there. And if I'm here for these constant amplitude load cases to plot such a difference between number of cycles, numerical and experimental, this means this is scatter around the regression line of our strain life curve. So this is constant amplitude scatter here, going there, and this is variable amplitude loading scatter. And my message is that, well, what is scatter here is scatter in material, and you can only do a better job if you do a probabilistic approach and put everything which has been deterministic here in my approach into some probabilistic framework. So seems to be everything solved, but this is far away from being so. The notch effect we considered by simply taking generalized Neubers rules and a notch fatigue factor. We did not deal with multi-axiality or thermomechanical loads. We did not cope with the problem of transient thermocyclic behavior. And what was astonishing for me is that if we want to arrive at highly accurate life prediction results, we have to use plasticity models which are able to take into account cycling hardening, cyclic softening, mean stress relaxation, and this and that. It's not the case that we couldn't do that. We could, but it takes a lot of effort to include that in previous, in following up research work. So, what remains here? We have identified sequence effect and taking into account in our modeling the sequence effect. Threshold behavior is one, and the delayed behavior of crack opening strains is the other item. And I didn't talk much about the temperature effect. As I said, our final version, I think it is hardly possible to increase its prediction accuracy for our batch of experimental results. And if you are interested in more details, there has appeared already one publication on that stuff. Finally, I thank those people who gave us the money, the German taxpayer especially. And again, my thanks go to our research partner at Fraunhofer IWM in Freiburg, especially Sophie Schackert and Christoph Schweitzer. Thank you.